Okay, not sure I needed to write all that, but it's so Watanabe 2010. So I guess a bit of a timeline is that, say, the gray book is 2000. So gray book, by gray book, I think I should say that gray book means algebraic geometry and statistical learning theory, the book. That's 2009, and then there's the green book, which is Mathematical Theory of Bayesian Statistics. That's 2018. So that is kind of an evolution of techniques here. And today I'm going to stick to the notation and technique presented in the paper. But I think the green book has updated sort of notation and sleeker presentation. And the quantities are defined a little bit differently. So if you're reading that, you might want to be aware a little bit. And the gray book provides sort of the foundational results that sort of feed into later works. So sort of most of the ideas and tedious calculation is done in the gray book, and the green book and this paper sort of uses those in a very crucial way, but with a lot more sort of conceptual stuff layered on top of that.
The orb is here, Edmund, if you want to attach.
Sure, let me do that. Should the speaker be in alt cam? Okay, so all right. Okay, so the sort of the technical goal today would be, I guess it's based on the audience. I guess it's worth to go through sort of the usual definition route, the setup of singular learning theory, as well as define some of those quantities, important quantities codes that is known as Bayes observables in this paper, and then define something called a generating function for the learning theory, and derive universal laws of learning theory from that, right? So, and there's a conceptual goal is kind of explaining some of the word choices above, right? So why do we use observables, and what's generating functions, and what's it going to do with learning, and universal law, and what is renormalization, renormalizability conditions, etc. So, but overarching an overarching theme will be link sort of stats learning, so statistical learning, to stats physics, and just based on the terms being in use, there's already some link there, and we will discuss. I don't think I can make it tight, but at least I think throughout the tedious calculation, I'll motivate the link here, and sort of discuss the idea of renormalization in learning machines. Right. I guess I will front load the following analogy. So I should say, let me use so I'm going to mention this just so that we have it at the back of our mind throughout the presentation, which is central limit theorem. So I'm not going to state it in its full generality, but I think in sort of conceptually, I'm going to state it in this way. So central limit theorem says that aggregating, I don't know how to spell, aggregating large number of independent random variables result in a Gaussian. Provided ... right? Provided some of the things hold. I guess I don't need to do ... here. I can say something like provided all of them has finite variance. Okay. Right. And there's a lot of generalization of this result. Let me draw a picture. So we have kind of a sort of space of distribution with finite variance. And then there is kind of a subspace of Gaussians. An important thing to note is that Gaussians are completely specified by their mean and variance, by two real numbers in the one-dimensional case, and I don't know, d plus d times d minus 1 and 2 real numbers in the d-dimensional case. But the point is that this is saying if you start off in this space, in this very, very large space, infinite dimensional space of distribution with finite variance, if you start doing this kind of summarizing or aggregating, and you have lots of independent realization, lots of particles, and then you start to say that I don't care about the details of each individual particles, what they are doing, and I only care about aggregates of them. And if you take increasing larger and larger aggregate of these independent random variables, then you will flow this process of aggregating ever larger number of independent random variable will flow you towards this much lower dimensional subspace, where only a few, by a few I mean just the mu and sigma details, a few sort of characteristic of the system survive. Everything else are quote unquote unimportant details. And the generalization of this central limit theorem. So
sorry to interrupt, Edmund, but it's getting a bit small, the writing down the bottom there.
Okay. Okay, that's.
It's
yeah,
fine.
okay.
You don't have to rewrite it or anything.
It's
just I just want to stop you from further converging to variance zero of your characters around their center.
Yeah, I can see that in the Occam view, that's very small. Okay, I will write larger. All right. But yeah, so the generalization of central limit theorem would be sort of stable diffusion. Stable diffusion. Sorry about that slip. But stable distributions. So where if you have heavier tail, so no finite variance, you flow to some other subspace, for example, right? Okay. Okay. So just there to, so that's an analogy that I will sort of hope everyone keep at the back of their mind. So I'm claiming that that's kind of a broad conceptual renormalization, the coarse graining of data resulting in a flow of model. By model, we mean the statistical distribution describing the data. That model, as you coarse grain, the model flow towards a fixed point. All right. Okay, let's start off with some non-conceptual and technical stuff. Right. So here's sort of revisiting SLT setups, and I guess it's good to go through this just one more time. So usually we have a true distribution. And we usually notate that as Q of X. That's sort of cordoned off from our world. That's something that we can never interact with directly, but we can. But we do know that we can only access it through the data that it generates, and we usually notate that as dn, and each individual data generated from it, we are the x's, and little n, it always means data set size. And we assume that the xi's are IID, so independent and identically distributed IID from Q of X. Right. And then the other component is, well, you have, humans, you. So we design or come up with a model, which is a parameterized family of distributions that are distribution in the same space with parameter space we call W, and it's parameterized by a subset of R to the D, and D will always be the parameter dimension. Right. And what is a learning machine? Well, a learning machine, well, it takes in the data and takes in the model that you design and spits out distribution. Well, the prediction. Spits out this prediction. So a good learning machine will have p hat close to q, close to the truth. And the theoretical properties of this diagram, of this learning machine is the setting of statistical learning theory, right? For what kind of model, what model works well for different types of learning machine, for what true distribution. That's kind of the general area of study of statistical learning. And in singular learning theory, at least in its current form, we are mostly concerned with the Bayesian learning machine. So what that means is that, so I just need to specify what is this p hat thing. And that p hat in the Bayesian learning machine means the Bayesian predictive distribution. So that's equal to well, it's saying that to produce to predict the probability of a given x, well, you can ask what's the probability of x for any of the distribution in the model, but each of them will have different kinds of performance, but we just average all of them, average all their answers. So this is, in machine learning term, this is called Bayesian model averaging, using the posterior. And here I'm using sort of physics notation here. Like this is like ensemble averaging. So already I'm sort of treating the Bayesian posterior as analogous to the Boltzmann distribution. Well, in explicit form, that's averaging this function with the Bayesian posterior. Where the posterior P of W given Dn is equal to 1 over the partition function of the evidence, e to the negative n, Ln of W, where Ln of W is the empirical log loss. So Zn is the evidence.
I think you need an I on your sum and maybe xi.
Thank you. That's capital Xi. And that thing there is a prior. Okay, so in my picture above, I don't really know where to put my prior. I guess it's like I'm conceptualizing it as part of the learning machine. It's part of that machine that it carries a bit of prior, or human can specify it, right? I guess it's important to note that in multiple places, Watanabe did mention that the prior, although it used the same word, doesn't really mean the usual thing of the prior being specifying a prior belief over the parameter space. It's really it's keeping that the status of the prior as well. Where does it appear in the formula? That's its status kind of thing. So frequently it's treating both model and prior on sort of equal ground. Okay. Please stop me if you have a question. Let's move to the next board. Okay, let's define some base observables. So the idea is that
it might actually be better if you move back a little bit so that this is the second board and people can keep seeing. Yeah, there's good. Yeah.
Okay, cool. Yeah.
Thanks.
Right. Nice. So, so think of this as
Can I ask you a question?
Yeah, yes, please.
Yes, in the previous slide, this Bayesian learning machine is p hat. So to get this p hat, the input you have is this model px given w, as well as this dataset dn. The dataset is used to construct this log, the empirical log function, right? Okay, so yeah, the dataset give you this ln w. Yeah, okay. And
yeah,
then
that's
you
correct.
integrate.
So, yeah.
Yes, then you get a go ahead.
Yeah, so I guess it's worth pointing out that this is not usually how Bayes' theorem is written. This is a convenient form for us to do mathematics later on. Like usually this is usually we have statistician will call this so e to the negative nln term here the likelihood. So this, so that's a function of w, and like if you unwind this, this is just the product over all the data like that, right?
Yeah.
By the way, I forgot there's a beta in here, and let me just put that in. So beta equal to 1, you get back the strict Bayesian learning, Bayesian posterior, and beta not equal to 1 is just a tempered posterior. So just another kind of learning machine. So this learning machine itself is parameterized by a beta.
You should probably put the beta in the partition function then too.
Thank you. There's an N beta here.
That's very legible.
Sorry, beta in here.
That's fine.
Yeah.
Yeah, I see then. M beta. Okay. Yes. Then this fits your picture of this learning machine. Okay.
Yeah.
Good. Thanks.
Yeah. I should probably also say that the reason I sort of conceptualize it like this is that, well, that learning, this is not much of a practical learning machine. Like this integration Bayesian model averaging, complete Bayesian model averaging is almost surely not achievable for neural network in practice. But that this machine could be something like, let's draw something from the posterior, or stochastic gradient descent or whatever, right? So you have a procedure that come out with p hat. That's your learning theory goes from that. Right. So in the next board, we want to define Bayes observables, and the term observable is sort of analogous to the observables in, I guess that's mostly used in quantum mechanics, but I guess the statistical physics also has the term state variables and analogous to that, like the number of particles, the volume, internal energy, entropy, etc. Yeah. I actually think that the observables that we are defining I'm writing all extrinsic state variables here. I think most of the things I'm going to define are intrinsic. Sorry, extensive versus intensive. But anyway, so okay, so we have the Bayes so training error. So this is equal to, well, we can sort of evaluate how good our p hat is. So remember, p hat is the Bayes average over W. So whenever you see an angle bracket and it's just averaging over anything that depends on W in it. So for each of the data point, we can, that's the prediction. So that's equal to p hat of xi. So if that particular W is really good, then that number will be very high. Take the log, take the negative, which means that instead of really high, we want it to be really low, and then average that over our data set. So that's our Bayes training loss. So it's a training loss for it's a log loss for average log loss for our p hat. And then there is another way of doing prediction, which is the Gibbs type learning machine.
What is that average over?
Which average?
Sorry, the inner one, the brackets.
So throughout this talk, bracket always means posterior averaging. Yeah. So we're thinking of the posterior like the Gibbs distribution and angle bracket for ensemble averaging. Right. So there's a Gibbs way of doing prediction, which is, let me randomly choose a W, and then just use that for, well, randomly choose it, choose a W. How do we do the randomness? Well, the randomness comes from the Bayesian posterior. So W with high posterior mass will be chosen more often. And then make the prediction on Xi using that one. And then that's the loss. Take the log, take the negative. That's the that's the log loss of that prediction. Average that over all your data set. That's an average log loss. Well, this is one realization of W. So since W comes from the Bayesian posterior, let's just average over the posterior. So that's the Gibbs training loss. Okay.
Ask you a question.
Yeah.
Can you sort of explain a little bit about this averaging?
Which, the angle bracket averaging?
Yeah.
So if you have
do you mean, Zhongtian, how would you actually do it? Or what it is?
Yeah, what it is and how to do it.
Okay.
Right. So if you have if your W is always drawn from the Bayesian posterior, so does this notation make sense to you?
Yeah.
Then if you have any function of W, f of W, well, now this is a random variable that depends on W. You can take the posterior average of that, which is equal to f of W and posterior integrate that over. So that's what it is.
Okay.
Does that make sense? Yeah.
I see. Yeah. So so the density function you take is the one you defined in the previous slides. Then
Correct.
you average this. Okay, good. Yeah.
Yeah, correct. Yeah.
The idea is meant to be that BT and GT are somehow things you might actually compute. And to do that, you would have to somehow draw samples from the Bayesian posterior. And to do that, you would use Markov chain Monte Carlo or some variant of that. That may be difficult, but in principle, you can do it.
So these are things that you can compute in practice. So using data set, really hard though. But you can actually compute it, right? It doesn't refer to the true distribution. That's kind of the point.
Yes. So right. Each data set will produce you this function on W, and then you
correct.
Then you average it using
correct.
that density.
Yeah.
Okay.
Yeah. So once you have the Bayesian learning machine, pin down your beta or something, then everything in here is just very difficult sums and integrals of the data set. With the data set as input and integrals over the parameter space. Right, and then there's the theoretical quantities, which is just replace all 1 on n and sum with expectation over the true distribution. And so replace that with that. Right. So those are theoretical quantities, right? Refer to Q. It should be noted that all of these, so even though on the right hand side, we have average over the X. We haven't averaged over data set, right? So these are still random variables. This still depends on this bracket here depends on, well, it's an average over the Bayesian posterior, and the Bayesian posterior itself is constructed from the data set, and the data set is random. So these are still random variables. Okay, and we have some other quantities. I should not have. So this is that red comment above still apply for the one below. This is also computable using data. So let me just write out the expression and okay, so the square goes inside and outside. So this should remind you of variance of, so empirical of, well, of negative log of the log loss. But because, well, let me just put it in, of the log loss, right? And because negative doesn't matter in variance. It's got squared away. And then there's, of course, the average version of that. So sorry, I said something wrong. So that's the variance, and it's not even empirical. It's not empirical. So it's under the posterior. Right. So so this whole thing is equal to variance under the posterior of negative log p x w. It's just that we average the variance over the data set. And here we just average, we do the same thing, except we take the data set average to the theoretical average. Again, the negative doesn't matter. Okay.
When you write that equality, so equality VW, I mean, the sum over I is not still there, or do you just mean the summand is equal to that?
Yeah, xi, yeah. Yeah, okay. So each term in the summand is equal to the variance of the log loss at xi.
Mm-hmm.
Yeah. Okay. I should also note that these quantities defined in this paper are slightly different from the one in the gray book. Those things in the gray book are normalized, right? So they are compared to where their values are compared to the truth or to the optimal distribution. So that's just a warning for reading, but it shouldn't affect us too much as long as we keep our be careful about our calculation. So there are some other theoretical quantities and sort of theoretical relationship to sort of classify models. So the first one is we have the first one is the expected log loss. Right, and well, that thing, so is expectation of a quantity that we have seen before, the data set version. Right. And we can normalize this with the entropy of the true distribution. I'm going to absorb the negative into one of the x. So that we have that becomes the KL divergence between the truth and the model at the distribution of the model at W, which is equal to L of W minus S. That in itself is an expectation of that in itself is normalized by the empirical version of the entropy, and just replace integral with sums of the data. Right. So this DKL is equal to 0 only if, so definition, truth Q of X is realizable by model PXW. Right, so that means there exists W0 in the parameter space such that Q of X equal to PXW naught. If not realizable, we turn instead to talking about not the truth itself, but to the optimum. So W naught will always denote, will always be defined as the set of parameters such that the log loss achieve its minimum. Right. So parameter space W optimum W naught, Q could be outside of W. Right. So now fix a W naught in this set of optimum parameters, and set P naught of X to be equal to the distribution at this optimum parameter. So just choose one. So this is, again, so realizable. Another way of saying that is that P naught of X is equal to Q. That's easy to see. But we also want, so definition, essential. Another property we could define is essential uniqueness, which is saying for all other optimal parameter in optimal parameter, the distribution is the same. So you could have different distribution achieving the same KL divergence between the distribution and the truth. but we don't want that for at least in the set of optimum distribution. We don't want that to happen. So this is called essential uniqueness. And we will assume this throughout this paper. Okay.
Sorry, I didn't get this context. Is essential uniqueness. It's saying that for all these true parameters.
Those are not true parameters. Those are optimal parameters.
Okay, optimal parameters. Then is P0. So it's P0 X will be the true distribution. Right?
No, P0 X is one optimal distribution. So I have fixed a W0. Pick one. Pick any one of them. Essential uniqueness is saying that it doesn't matter which one I pick, which optimal parameter I pick. It will all define the same distribution. That's essential uniqueness.
I see. Okay.
Yeah.
Okay. So this is not realizable. This notion is defined.
Yeah. Yeah.
Okay.
Correct. Yeah. Okay. Then we can use that optimal distribution to define some normalized quantity. So previously we have this function that measures the loss at a particular parameter value. We normalize that and call it f. Yeah. I wrote something wrong in my notes. That should be normalized by the optimal, not normalized by the truth. So if you are reading the gray book, P0 is just Q. If you're reading the green book, or in the not unrealizable setting, just swap all quantities that reference to Q in the theoretical quantities, and replace that by P0. So L and W.
By the way,
yeah.
There is a typo in the essential uniqueness. Maybe you want to put at P X given W0 prime.
Thank you. Yeah, that's very important. I mean, yeah. Okay, cool. W0 prime. Thank you. Right. So Ln becomes Kn, and it's defined to be. So I'm using the same letters. The K's is the same, except now the Q's are replaced by P0. So L of W sort of normalized to K of W, which is the main quantity of interest. Well, L0, what happened there? L0 is equal to L, the average loss at the chosen parameter, but it doesn't really matter which parameter we choose. It's just all equal to the arc mean. So L0 is actually a constant on W0. Okay, and the evidence normalized to that. So instead of integrating with NLN, we the exponent becomes Kn instead. Okay. Okay, and so with all this, we say that the true distribution is regular for P of X W if the optimal set is a singleton. So nothing about realizable here. So it's regular for W0 if the optimal set is a singleton, and the Hessian of L at W0 is positive definite. And singular for the model otherwise. Okay, this is a bit boring and that took a lot of time, and I think this is the first possibly new thing. Let's go ahead and define the generating function for a learning question. So the idea of generating function, I think we are familiar with. We encode quantities that we care about as coefficients in the power series. Well, I'm going to write down the definition. So the generating function with parameter alpha is equal to sound remark. So that expectation means so in the paper it says that it's an expectation over data set. So the data set features in here, right? The data set goes into constructing that Kn variable. So that Kn is a random variable of the data set. And then there is this new test variable here, which is a new data point. And we want to know the prediction on that new testing point. So I guess the data set is a training data set, and this is the testing data set. X without substrate is a testing data set. And this expectation is over O n plus 1 number of the of data. So the original n plus a new test data set. And I'm going to be explicit about that and say that it's actually taken in this order. So the inner, like everything here is under Mao assumption. These are all commute. They can commute, and there are IDs. And E sub n always means expectation over the entire data set. Right. So, but in the Green Book, another thing, a different expression is defined, is in the Green Book, sort of a G n of alpha is defined as the cumulant generating function of this random variable. Okay, what's a cumulant generating function? Well, cumulant generating function for any random variable y is equal to log expectation over the log of y, alpha y. So that's the moment generating function, and cumulant generating function is just a log of the moment generating function. Well, it encodes so moment generating function encodes the moments, and the first moment is the mean, the second moment is related to the variance, third moment, etc. Cumulant, well, the first first cumulant is the mean, second moment is actually the variance, and higher moments, higher cumulants actually are different, not easily interpretable. And there's a statistical physics connection if we are using the cumulative generating function. I should complete the thought before. So I think the Green Book way is more natural, just to define it as a cumulative generating function of fx. That's because so it's a cumulative generating function of f of x under the posterior. And you can see in the above expression here, this is actually equal to, let me write it here. This is equal to the expectation over negative log of the posterior average e to the negative alpha f xw. Well, except it's not quite right, because the normalizing, the evidence, the normalizing constant is not there. And if you put it back in, then you get the right thing. And in the Green Book, it doesn't immediately take the expectation over all data set to keep the exposition, I think, a bit slicker. So almost equal. Anyway, the statistical physics connection is that we have W is like the microscopic variables. By the way, this is my interpretation. If someone wants to dispute that, please do, because as I said, this is not tight. And we have, let's define Hn to be n kn of W. So just removing the 1 on n averaging before. That's like the Hamiltonian. HW in statistical physics. The posterior, well, if you use Hn, that looks like, except there is a buff, the prior there, but it's like the so equilibrium distribution or Boltzmann. Well, and then the CGF of f of xw at alpha, that, if you use the Green Book formulation, that looks a lot like the partition function. Which is z equal to, in statistical physics, is equal to 1 on beta log e to the negative bh.
What's
so
H?
That's H is the Hamiltonian.
Where did the alpha go?
Right, I guess alpha is beta. Yeah, so, okay. So in physics, you differentiate respect to beta to get the usual, to get the quantities that the state variables that we want, the energy and etc. So in moment generating function, you differentiate respect to alpha. So I guess the connection here is like alpha is beta, and then the beta we use for inverse temperature. That's we use for temperature in our posterior distribution. That's something else.
Mm-hmm.
Yeah. So yeah, there's a bit of inconsistency there, right? So
still useful dictionary. Thanks.
Mm-hmm. Okay. Okay. So I'm going to spend some time just computing with this and see why we care about why we define this function. Let me walk to the next set of boards. All right, let me. So let's just start computing with this function. So that's equal to en ex negative log So I'm just reproducing this here in a sort of rewriting in a slightly different form. Just to make the fact that it is a posterior average very, very clear. So if you just multiply and divide by the normalized evidence, you can rewrite this as think of multiplying and dividing by that, and taking that inside here, that becomes a posterior average, and then you acquire another term out the front. So this becomes posterior average plus right, and okay, first of all, this the second term, the EX, doesn't matter because the random variable inside doesn't depend on it. And if you recognize that form, that's just the free energy, well, the normalized free energy. Yeah, so that second term is the expectation of the free energy, normalized free energy. All right, some value of interest. So Fn evaluate at 0. Well, you so that term goes away, and you are just evaluating the evidence, and that's the free energy. That's the second term, right? So this term is actually equal to Fn, script Fn at 0. So and this is equal to right. Okay. What about Fn1? At 1, well, that's equal to, so, oh, I shouldn't have put this here. So substitute alpha equal to 1 in there, you get x of negative log the average of e to the okay. I'm going to expand the f function. And O plus Fn of 0, because there is that annoying second term there. Well, this is equal to the E and logs cancel, and P naught doesn't depend on W. I should just annotate this little n everywhere in the bracket, because that will be important later. So the P naught doesn't depend on W, so it is not affected by the posterior average. So you can put it out, and then it becomes so if you pull it out and then take the negative log of P naught of x, negative log of that term, and you take the average over the x, average over the truth using the true distribution, well, you get L0. You get negative L0. So that's from pulling out the P naught. And then what's left in the bracket is just plus en ex of negative log. That's what's left in the bracket. Well, and this inside is BG. So that's equal to, so we have our equation. So therefore, data average of the Bayesian generalization error is equal to L0 plus did I get this right? There minus. Oh yeah. So Fn1 minus Fn0. Okay. All right. So you can continue in this fashion and derive formulas about the Bayes observables in terms of this generating function evaluated at various points. So let me just not do too much more calculation. You can see some of the details in the notes. But let me sort of write out a few. So that's equal to the training version. Well, the training version it is Fn minus 1 plus beta minus 1 at beta. So the logic behind that is that to get a training version, you actually, I'll actually do a calculation for the Gibbs training error, and that will illustrate the idea of how you do that. But let's go to the next board. So what's important about generating function is that you can differentiate and extract quantities. Well, the first derivative of the generating function is, okay, under the assumption that you can exchange derivative and the expectation operators, and under our usual assumption where main theorems of singular learning theory goes true, that will be true. So you bring the derivative into the expectation integrals and differentiate the logs, and that gives.
Sorry to interrupt, Edmund.
Yep.
This is really valuable, and I hope you finish. But I'm going to have to go. I'll leave the recording going. It's just I've just gotten a message, and I have to jump up. So just go as long as you like, and finish what you have to say, and the recording will catch it.
Okay. Cool.
Yeah. Thanks a lot. I'll see you later.
No worries. I'll promise to stop by 5:30. Okay, so you get that expression, and as with most cumulative generating function or generating function, you want to evaluate the so eventually you want to evaluate its Taylor series at 0. So let's evaluate the first derivative at 0. What you get is right, and quickly to the second derivative. Use the product rule or the quotient rule. So if you do the quotient rule, you will see, that you bring down the f by derivative by alpha, and the second one you get the average of that squared instead, and that's very reminiscent of a variance formula. So if you evaluate at 0, you get, what do you get? You get excitation at negative f squared plus f excitation squared. Well, that's equal to negative of E of YG. Remember, that's one of our base of observable, the functional variance. It's called the functional variance. Okay. Okay. I'm going to do just one more to illustrate a few more tricks that's involved in getting these quantities, and then we are going to go to the sort of general theorems about this. So next we want to show, so we want to show the next formula, which is the Gibbs training formula. The training version is always is usually difficult. It's usually more difficult. Just to remind ourselves what that is, that's equal to what's the Gibbs training formula again? It's equal to that. Well, let's simplify that a little bit again. Oh, by the way, so this is E. So there's E, N, and EX in there, but but G of T itself doesn't depend on that new testing data set. So the EX drops out. N, this is a finite sum, so just pull it out. So you can pull out the finite sum over the posterior averaging and the averaging over the data set, but the posterior average and the data set average, they definitely do not commute, right? Because the posterior itself is a random variable of the data, so you can't push it in any further. What you can still observe is that the xi, so since xi's are IID, so they all come from the same distribution, and they are all independent. It means that let's look at each term in the summand. Well, well, it means that there's each term, after you take expectation over the entire data set, all those terms is the same. So that is actually equal to -1 on n times n times en of log of pxi given w n for any I, right? So every term in there is a term for a different xi, but every term, the posterior average depends on the entire data set, but internally inside that, if you write out all of them, they are completely interchangeable. So for any I, that's the same term. So you just get the same number times n, and the n cancel. So the whole thing is equal to negative en log. And let me just choose an I. Let me just choose it to be xn there. Okay. All right. So we want to prove that we want to show that this GT is equal to is related to the generating function is equal to L0 plus the first derivative of a generating function at n minus 1 beta, and evaluated at beta. So let's just compute. First derivative at beta. So we have our expression of the first derivative there. So substituting n minus 1. So that's n minus 1. And then you have that, but be careful that this is average over the posterior is now constructed with only n minus 1. There's an n dependency in the posterior itself. So you only use n minus 1. You don't use the last data point. Okay, and then you just start unwinding definition. And well, remember what f of x w is? That's the log quotient of the truth over the model. And again, we use the same trick. The truth doesn't depend on the model parameter, therefore you can be pulled out from the posterior average. So you get a log p naught x here. But you have another term. That's the numerator. Again, those are all n minus 1. And let's look at what the bottom term. Well, the bottom term is equal to so make the exponential and the log cancel. You get to the power of beta divided by the optimal distribution to the power of beta n minus 1. Well, again, the optimal distribution doesn't depend on the model parameter, so you can be pulled out. And this term up here, well, we are going to take okay, so this term here, so what is that equal to? That's equal to, well, that term is the same as the numerator, right? So so that term and the numerator completely cancels. So our first term here is just this term. And what is that term? After taking expectation by ex, you get the L0, right? that's negative L0. So that's the first term handled. Minus, so what's the second term? The second term is equal to, or the numerator is pxw to the power of beta. That comes from this exponential here. Log pxw n minus 1. Well, it's divided by the numerator, but let me so divided by the numerator, pxw to the beta. Now, the trick is to see that this term, so what is this term? This term is equal to, so I'm going to write the posterior in the usual way without using the exponential. So that's I equal to 1 to n minus 1 prior dw. And, well, these are xi. Okay, so so if you okay. So that's equal to, the idea is that you absorb this inside here, and what you get is you are missing the xn term, but you add in another the test data term, which is of the same with the same distribution, and that recovers the evidence for Zn, right? So that's equal to so that's actually equal to Zn. I wrote something different in my notes, so I think this is the correct logic though. Okay, and then there's this thing to care about, which is, well, this is En, but without the expectation over the entire data set, but without the last one. But you can replace that with, you can sort of treat the new test data as training data, as the as playing the role of Xn. And if you write out this integral here, what you get is negative L0 minus En of log P Xn W. And now this is posterior average over On. Okay, I don't think that's very clear. So the idea is that you write out the integral and notice the symmetry between the test data and the last data point, and you can and also remember that you are taking averages over you are later on taking averages over the IID data random variable anyway, so you can treat them in equal flip, and that recover GOT. Sorry, that's not very clear, but I think you should just write out the integral, and I'll make sorry, I think we might be a bit running out a little bit of time, but this, I think I'll just make this last point, which is that in the formulas we have so what do we have at the moment? We have E of Bg is equal to L0 plus Fn1 minus Fn at 0. And then we have similar things. If you push through the calculation, you have, so keep track of how many variables are there in the right-hand side. So some of this we didn't calculate, but the calculation isn't very hard. Some of them are harder. That's wrong. That is beta. The second derivative up here, as you can see, that's the second, since the y are variances, and that's related to the second moment, the second derivative, therefore. Okay, so we have all this kind of formula. All this formula, but it looks like we have just replaced 6 formula with 6 variables and express it in terms of 1, 2, 3, 4, 5, 6, 7, 8, 9 variables. But the trick is, if you do Taylor expansion, which is why we are defining generating function in the first place. If you do the Taylor expansion, so by Taylor's theorem, so we don't actually need it to be convergent, to have a convergent power series. We just need, if this function is 3 times continuously differentiable, then for O(n), for O beta, there exists an alpha star. So that's Taylor's theorem with a remainder term inside. So inside the region that I want to evaluate this Taylor series. Well, looking at the quantities above, I care about starting from 0, and there's 1. The largest is 1 plus beta. So there's an alpha star in that region such that F0 alpha plus forgot about the half alpha square plus 1/6 3 and alpha star for the last remainder term, alpha cube. So we have this equality, and you can replace some of these F1s with the corresponding Taylor series approximations, provided so if this remainder term there, the supremum over all possible alpha stars in that interval is of little o of asymptotic order smaller than n to the gamma. Well, then you can start to replace, for example, F n of 1 by just the first 3 terms. With a penalty of 1 on n to the gamma inaccuracy. And okay, but there is also the fn minus 1's terms. So we also need the fact that the difference between those is also little of 1 on n to the gamma. Sorry, I think I will refer you to the notes and the paper for the precise conditions. But the main idea is that the remainder term is of order smaller than n to the gamma for some gamma, and the difference between n minus 1 and fn is smaller than the same order as well. And then you can, which means that the 6 variables, the 6 observable on the right, now reduce down to, it depends only on 3 variables: that variable, and that variable. Right. And so I think I'm just going to say sort of the point of all this verbally. So now we actually have a sort of a similar situation to the central limit theorem, where there are some details if you have larger and larger data set and you aggregate more and more of them, these variables that the base observable that depends on the details of the triple, the truth, the model, and the prior. So they depends on everything in the triple, but as n goes to when n is large enough, somehow this 6 variable only depends on 3 of them, which means that there is actually a linear relationship between them, which is therefore called the equation of states, which in analogy to physics, there's obviously
can you move to the right a little bit, walk to the right a little bit?
Oh yeah, thank you.
Yeah.
So these are the equation of states. And the idea is that in statistical physics, the sort of details of the system, so whether or not we are talking about the ideal gas or monoatomic ideal gas or molecules that can be treated, and we are in a low enough regime, energy regime that the internal degrees of freedom of the molecule doesn't matter, or we are talking about an Ising model and things like that. So all that details doesn't matter as long like they satisfy the same thermodynamics properties. They have the same thermodynamics properties if they satisfy the same equation of states. So in learning model, we have this kind of a similar situation where the details of the learning machine and the detail of the truth doesn't matter as long as they have the same, well, as long as they have the same L naught, F naught, and F naught. Right, so these are the variables that sort of control the learning behavior. That's why I thought that's weird. Actually, if you write out the if you do the Taylor series expansion and substitute it back in, the first the Fn naught sort of cancels. So it depends only on these 3 things. And the result in the gray book and also the result in this in the later section of this paper, the renormalizability condition says that if you're renormalizable, then gamma is equal to 1, meaning that you satisfy the order condition just now with gamma equal to 1, and you are defined by, and in that case, you have f prime at 0 equal to lambda over beta plus nu, plus nu, and that is equal to 2 nu over beta, where lambda is the RLCT and nu is another birational invariance called the stochastic. Actually, what is it called again? It's a variance term. Right. So okay, I think I'm going to stop here, and we can talk about implication next time, and the rest of it. Sorry for going way over time. Any questions?
Can I ask you?
Yeah.
How about this Fn prime beta?
Yeah. So if you go back to, let's go back to the second to last board. The idea is that you let's say we want to let's re-express the second term here. So how do we do that? So you have so fn minus 1 1 plus beta. Well, what's that equal to? According to the Taylor series, that's equal to fn minus 1 at 0 plus fn minus 1 at 0 times 1 plus beta plus that's a prime. That's the derivative. Second derivative n minus 1 0 at 1 plus beta square on 2. And then plus, because of the learnability assumption, plus an error that is smaller than 1 on n to the gamma. You do the same thing for fn minus 1 of beta. Actually, let's forget that first. You first say that using the additional assumption, which is this assumption here, that the difference between the n minus 1 and n version is also of order n1 on n to the gamma. You can just erase the order n minus 1 in here with the same error term. And then you do the same for the second term here. Take that difference, and then you now express everything in terms of that term and that term, right? That's the idea.
Okay.
So only these two terms matter. The first term actually always cancels out because that's the expectation of free energy, if you remember.
Okay. Yeah. So just for the whole story. So you want to know this 6 variable, this observable. That's the thing we want to know. Then this. Go ahead.
Yeah. So go on. You can tell me your interpretation.
This generating function makes this 6 variable into this 3.
Yes. So in fact, so if you have a different truth or a different model, meaning a different learning statistical learning problem, then you will have a different generating function, right? The generating function depends on the truth, depends on the model, depends on the prior. And if you do a Taylor expansion up to a high order, up to order 100, then you have this fn prime, the derivative of fn 100 of them. But here the learnability assumption is saying, by the time you get to order 3, you are in the 1 on n regime, meaning you are decaying, right? If you are talking about large number of particles, large number of training data, then that starts to not matter. So which means that only the first 3 terms matter. And that means that any statistical learning problem with the same, it doesn't need to be the same generating function. It just needs to match match the tree jet. of the of the cumulative generating function. So if your Taylor series match up to 3 terms, then you are in the same universality class. Like if you coarse grain in the sense of taking larger and larger data set, looking at larger and larger realization, then you flow to the same fixed point. And those fixed points so we didn't discuss this today, but those fixed points are parameterized. Like the central limit theorem is parameterized by the mean and covariance of the Gaussian. Well, the fixed point for our learning theory is parameterized if you have gamma equal to 1, is parameterized by the RLCT and that new term, that variance term, by two numbers, and those numbers are so you those two numbers characterize the fixed point of this renormalization flow. I'm using renormalization in a very conceptual, non-rigorous way, which I guess the physics people does it as well. So, right.
Okay.
Yeah. Any other question? Oh, so I'm pointing out the fact that there is 6 observable and 3 just depending on 3 terms modulo some irrelevant error. I'm pointing that out as evidence that we have reduced complexity. So before you need 6 number to describe parts of the learning machine behavior. Now you only need 3.
Right.
But in general, like I don't know, you can define some other observables that cannot be expressed by combination of these things. But I'm just pointing out that there's evidence of simplification. Is what I'm saying.
Okay, let's see. So it's like the central limit theorem. In that case, the thing we work with random variable.
Yeah.
In this case, is each of this model, right?
Yeah, I think in this case it's a triple. Is the truth model prior?
Yeah,
triple.
truth. This machine. Sorry, this machine. Each machine will give you is parameterized by this generating function.
Yeah.
Okay. And just I start with a machine satisfy this condition. I compute this Fn, and as n goes to larger and larger, it's like the central limit theorem. It's become Gaussian, and in this case, it's like this the thing determined by these 3 variable Fn not L not Fn prime and Fn double prime.
Yeah.
Okay.
So I'm not saying in this case that they converge to the same distribution. They don't, but they converge to distribution whose main order term match. So the main order term is which is why we mentioned the RLCT because that's the main order term.
Yeah, I'm not the distribution. It's like this machine.
Yeah.
Yeah. Okay.
The base observables sort of match.
I see. Yeah, I think that's what I want to ask.
Okay. Yeah. Okay. So the rest of the paper actually goes into cases where the condition of learnability those conditions, the decay condition it's actually met. So realizable case, that's easy. Sorry, regular case, easy. Singular realizable, that's in the gray book. Singular, non-realizable, but something called renormalizable, which is why we call it renormalizable. That's handled in the green book and handled in this paper. And other cases, well, that's still up to debate.
Okay.
Other more general cases is up to debate. Not debate, pending research. Yeah. Okay.
Thank you.
No worries.
Thanks,
Any other? No worries. Thanks for staying.
See you next week.
See you.